Okay, so let's continue talk about lipids. And we finished talk about here at the opening remarks, but we want to continue to mention something. So we talk about animal oils. That's one of the resource for the fatty acids and the depot fat. So depot fat we have tallow and lard. Generally speaking, the depot fat is approximately 36% is unsaturated fatty acids versus more than 60% is saturated fatty acids. So that's something we want to say. And also, we mentioned about the milk fat. And we also talk about cis and trans configuration of the fatty acids. In the milk fat, there is limited amount, around 2 to 6%. Some people will say 3 to 5%. Those are trans fatty acids. The reason is obvious because of the cow has microbial lumen nutrition cycles. You can say that. That's kind of interesting is recently we talk about the egg. So egg fatty acids. People did some of the research, and they find that they are dominant with basically 3 different types of the fatty acids, which is palmitic acids. So palmitic acids, we already learned that it is a saturated fatty acids is C16 and 0, no double bonds, and oleic acids, that is C18, 1 double bonds, and linoleic acid, that is C18, 2, and 2 double bonds, unsaturated fatty acids. And recently, because of the avian flu, so the egg price is increased. But if you noticed at a market, the egg price is always very high for one type of the egg, which is, they say, the egg is rich in omega-3. Now, why they can do that? Why the egg products will be rich in omega-3? Because of the feeds. And the feeds, they feed them very special, have flax oil, the products called flax oil there, and then let the chicken produce the egg, which is rich in high amount of the omega-3. So generally speaking, the egg could be $2 to $3, 1 dozen, and if you have omega-3 components, could be up to $5 or $6 per dozen eggs. So just these are just want to mention briefly. Now there is some 2 things we want to continue to talk about. Number 1 is unsaturated fatty acids. There is one index, we haven't talked about that, but it is important. It's called iodine value. So what this means? We could write a standard formula for unsaturated fatty acids is like this, O1 and O2. And this one can react with an iodine. So the iodine will be added there, then becomes what type of the products? Obviously, you can see the double bonds, the iodine could go there, so will become O1, CH, O1, and 2 iodine can add it. this comes out with the iodine value. So obviously we know saturated fatty acids, the iodine value is 0. And the one, Ian will talk very quick, talk about cocoa butter. The iodine value is around 30 to 40. And if we have poly saturated fatty acids, their iodine value could be up to more than 130. Now, we are more important is not this single iodine value. Using the iodine value, we are more important is the ratio, because ratio can be the ratio of unsaturated fatty acids compared to saturated fatty acids can use to decide the lipids oxidation possibility and rate. This related to the shelf life and also related to the packaging. Now, lipids oxidation is another major chapter of food chemistry, and we will talk about that later on after the spring break. So we mentioned polyunsaturated fatty acids. This could be the soy oil, and that could be up to more than 130. Okay, so these are the things we want to talk. The unsaturated fatty acids, the iodine value. Another thing we want to mention here is important. It's easier to understand is we talk about melting points of fatty acids. And we can just do the conclusion, and everybody can understand it very well. So we have high, we have low. So the first thing first is everybody knows short chain fatty acids, it's always have low melting points. And long chain fatty acids has higher melting points. We know that. Cis configuration have lower melting points, and trans configuration has higher melting points. The reason is that this you will get to is a double bonds, which is called a curvature. The curvature there for the CH double bond CH could make it difficult to become a crystal. The fatty acid is crystal, so the melting point is easier to be is relatively increased. Another thing we also can do the comparison is saturated fatty acids versus unsaturated fatty acids. Now, obviously, saturated fatty acids have a higher melting points, and unsaturated fatty acids have a lower melting points. So this alone, we could make a table to explain and the melting points, because it's an important index when we talk about the fatty acids during the food processing. So we talk about the fatty acids, and we can do some conclusion, a review. So we have a meso ends. So you go ahead and have a very long CH2 chain, carbon hydrogen chain, and end with COOH, a carboxy end. Then we talk about nomenclature, if we are counting from the CH3 end, methyl end, we call this the omega system. And if we are counting from the carboxy end, we call this a delta system. And we also introduce you lots of the common, widely recognized the fatty acids. So for example, we have C10,0, this is carboxylic acids. And we have C16,0, that is palmitic acid. And we also have a C18,0, that is stearic acid. And then we also mentioned the three major unsaturated fatty acids with oleic acids, C18,1 and C18,2, linoleic acids, and the last one, C18,3, linolenic acid. So, and then we talk about also the trans versus cis. It's coming from the hydrogenation. Okay, we mentioned about the saturated versus unsaturated. So that's what we talk. Now, today, we want to go to the next one, which is triglycerides. So what is that? Triglycerides and the fatty acids could work, which is glycerides, and the fatty acids will be work. So what is triglycerides? OH, C, H, OH, C, H, H, OH. And then we here has C, H, R1, C, O, OH, R2, and here we have R3. And these, they could be combined to have the reaction. Okay, how they have the reaction? Obviously, they're gonna lose the water. 3 molecules of water. So finally, what they become? CH. O1. O2. And O3. That's triglycerides. Have something want to say. First of all, we want to talk about this guy. So we move this one here. What did you find? So what's so special of this one, the glycerol? So glycerides. What's so special? It's very interesting. The center is a carbon C. And the two ends. So carbon C is surrounded by, we can say, 4 different chemicals. What are the 4 different chemicals? H, OH, this guy, and that guy. So how we say it? 2 out of 4 are identical. So what this means? You can see there. We're going down literally. This is a chiral C. No problem about that. But the chiral C is a little bit different from what we talk about. The amino acid. Amino acids, The 4 different of these are different, except for glycine. Here you see 2 out of the 4 are identical, so it becomes what type of thing could happen? Central C, when you here, you have OH2, go here, you have OH2, then on top, you have CH2, OH goes here, CH2OH. Therefore, what could happen? It looks like a mirror. We call them, and here will generate. That's a different type of the isomerization because of these 2 other signals. Okay, so that's something we are going to briefly mention. And then, in your textbook, they also want to say something very special with this C. Sometimes they say this like this, like you are flying out of the airport, something like that, flying out of the airport. Sorry, it should be the opposite direction. That's the wedge form and the large form. So this like you are flying out of the airport. And this is you go back. So we do like this. This is also, we can say, they're going back. So you can do like that. So wedge form and the large form. Okay, so these are the chemistry we just briefly mentioned. Now, what we are interested in is right here. Is R1, R2, and R3. This is called triglycerides. But in the normal life, you should know it could be only R1. It could be R1 and R2. These we call the mono or diglycerides. These are also important, but basically we don't eat that. They are using as an emulsifier during the food processing. So we will mention about that, but triglycerides we use it as a food products. So this is something we want to say. Now, more important is, when you have here, let's draw this on the top. When you goes to here, you have this R1, R2, and R3. This gives you 3 different positions. We also label them SN1, SN2, and SN3. So what is SM means? Stereo specific number. The location and the position and different type of the fatty acids, it is important and will have physical or chemical characteristics. So very interesting, we can give you some examples. We talk about the lard. So lard, what it looks like, it is very interesting. The SN1 and the SN3 position, it is unsaturated fatty acids. It could be oleic acids. There could be oleic acids. And in the middle is palmitic acids. So this means this could be C18-1, C18-1, and middle is C16-0. And makes this very interesting. Lard is a major Asian cuisine, manufacturing oils, which when cooking, you fry, you're using lard. And surprisingly, compared to the taro, There some of the researchers find if you eat a lard in the appropriate amount, it actually will protect the cardiovascular disease. The reason is the standard formula of the lard is have a high amount of the oleic acids here. So that's a very interesting topic. But of course, the lard coming from different resource of the pigs, of the hogs, there will be different amount. But just want to let you know, they have a high amount of the unsaturated fatty acids, so make it very, we call it a very researchable, the thing we can look for. But taro basically is composed by O1, O2, O3 is stearic acids. That's a saturated fatty acids. So this is the thing we want to talk. Now Ian is here. He want to talk about the manufacturing of the chocolate. So chocolate, we also want to say that the chocolate is interesting. So what is the chocolate make from cocoa butter? Now what is the three location of these cocoa butter, the fatty acids? At the middle is oleic acids. C18-1. Then the stereospecific number 1, the position is palmitic acids. That's a saturated fatty acids. And go down in the stereospecific number 3, that is stearic acids. So that is C18-1. This thing, make it interesting. Did you feel chocolate is a very magic food? Why? It is solid at room temperature, let's say 25 degrees Celsius. But when you put in the mouth, we can say it's a human mouth temperature, close to 35 to 37 degrees Celsius. What happened? It's melted. Is that be magic? There's something? Because usually it's not happen like that. So that's why it's a creative thing in the history, back when the first people using cocoa butter to make chocolate. And later on they find their specific formula, they find it's very, very interesting. That's characteristics. Now, of course, if the oleic acids in the stereospecific number 2, you replace it, we call it a lipid esterification. We'll talk about later on. Then maybe the characteristics will change. Sometimes the stearic acids, if it's replaced, you may have a blooming happens. You have a migration of the fatty acids outside of the chocolate. Then looks like it's a white area is there. So these are the things is interesting to look for. So we give you 2 examples. What we want to say is that in the history, back in 1950s, people proposed, which is the scientist called Hilderich. He proposed the O1, O2, and O3 are even distributed. So he gave the formula, like if it's GAX2, GAX3, and GA3, then the components will be, this is around 35 more percent, this is around 70 more percent, and this is more than 70 more percent. He thinks everything is evenly distributed mathematically, but later on people do research, find different products. They have their specific location is characterized by certain fatty acids. So they call it conditional restricted. And who is the person find that? Is Van der Waal. So it's very interesting, and that's some of the things you're looking for all the time. But I know right now we can, using the biotechnology, we can know the sequencing of these fatty acids and how they connected together. So let me see the time right now. Yeah, we get close to. The other things we also want to mention, one thing is the vegetable oil. Because vegetable oil we talk about a lot. Vegetable oil, what happened is this SN number 2, this is usually, it's a polyunsaturated fatty acids. And then the SN1 and SN3, usually it is saturated fatty acids. So these are the things I just want to tell you, those 3 locations, and a lot of the research can be done. If we use esterification, these components, if they change, then the characteristics of for the product certainly will be changed. So this is something good to know. The last thing is we talk about the nomenclature, which means a label, which means a name. So it depends if we know R1 is palmitic acid, if R2 is oleic acid, then R3 is linolenic acid, linoleic acid. So how we name it? We will be change the terminology. Here the IC, we change it to OYL. So we can say 1 palmitoyl 2 oleic and 3 linoleic. So just want to let you know, but sometimes we don't know the specific stereospecific number. So we can delete 1, 2, 3, we just say the components. Also sometimes we know they are very uniform, only one fatty acids. Let's say taro, we only have stearic acids, regardless of what is the location. We can just say SSS. And this means stearic acid. And sometimes we know there is oleic acid there, so we could write SOS right in the middle. That is oleic acids. Sometimes we don't know the components, but we know it is saturated or unsaturated, so we could write SSS. And here the S means saturated fatty acids. And sometimes we know, like we mentioned about the oil, the plant oil, the middle is polyunsaturated fatty acids, so you could write SUS. Then this U means unsaturated fatty acids. Certainly this U means the U at the arm. Okay? So these are something we briefly talk about. But I want you to be familiar with the structure, because when back from the spring break, we will talk next major chapter is lipids oxidation, or we call it auto-oxidation. We will go back to talk about the structure. We will go back using oleic acids, linoleic acid, and linolenic acids to talk about the different scenarios. So we'd better know the structure of those 3, because that's a huge chance and the model for talk about lipids oxidation. Okay? So I have been finished here, and Ian will talk about the manufacturing of the chocolate.
I'm not as good as Shen, so I need a PowerPoint.
Yeah, sure.
But while we wait for letting it warm up, we're going to taste some chocolate. Who here has had single origin chocolate before? Single origin, like the beans came from one farm, one place. I think I gave you some.
Belize. I have Belize.
Belize?
Yeah.
Wow, I didn't give you some. So I have some from Madagascar and some from Bolivia. We're going to taste the Madagascar first.
Can you make
You're welcome. So I suggest put it in your mouth and let it melt and kind of work it around your palate and just kind of experience it. The tasting notes on this one are obviously chocolate, but like there's a really prevalent like raspberry, a lot of malic and citric acid present in this bean, so it will taste quite tart compared to most chocolates. I'll get into the chemistry as to why those things happen, but the reason this Hershey's doesn't taste like this is because Hershey's is mixed origin, meaning the beans come from multiple different places, multiple farms, and so the really unique flavors and intricacies kind of get convoluted and lost. And then also, if you look at the label of a Hershey's bar, they can add like vanillin, which is, as we know, an aromatic compound, tastes like vanilla. They can add more cocoa butter to adjust the fluidity. They can add a lot of different things. The only ingredients I use in this chocolate is sugar and the bean. So there are no other adulterants, there's no other flavoring agents, there's nothing else. When you all are done, I have another one. The other one is actually my very favorite. I'll give it to you before this starts, you can eat it whatever you want. So this tasting notes will be like a very buttery pastry on the palate, almost like a croissant. And then it will kind of translate to like a limey, zesty tang. And that's the malic acid. And then it will transform to just like, I call it like a hug for your taste buds, just like the richest, most beautiful, fudgy chocolate you've ever had in your life. It almost has milk chocolate vibes, but it is not milk chocolate. Both these chocolates are 70%. So, like Shen said, chocolate is quite magical. As we all know, like who doesn't like chocolate, right? Very few people. And, geez, this might not work. Doesn't want to work for me. So, chocolate comes from the tree Theobroma cacao. It's a tropical evergreen tree. It's typically grown in like South America, the very central part of Africa, Ivory Coast. From this tree, you can see the pods, which are these really cool looking football shaped fruits. Inside the pod, we get the pulp surrounded by the bean. These are some beans. If you've never seen cocoa beans before, I'll pass it around, you can pass it around. Feel free to try one if you want. That's an Ivory Coast bean. Perfectly safe to eat. But it's totally unsweetened, so obviously it's just very rich chocolate flavor. The bean, dried fermented roasted, looks like that. And then paste would be that ground down to a chocolate-like substance. And from that, we can kind of press out the butter, and then we have the cocoa solids and the cocoa butter. I keep trying to change the slides with this. So the process, trees grow pods. Pods can contain beans. These are what the beans look like. The white substance is the pulp. That's super important for the anaerobic yeast and bacterial reactions that create the beautiful flavors we enjoy. Beans are fermented, dried, and roasted, as I said. Roasted beans are shelled and winnowed, creating nibs, and you probably have seen those on like acai bowls or like in smoothies. You can put cocoa nibs. Those nibs are ground and melange, which is like the refining process to create a liqueur. Chocolate liqueur is conked and tempered to make the wonderful thing we know as chocolate. Who knows? Have you all gone with approximate composition? You know what approximate composition is? Yeah? Okay. So typically, these are just different growing origins, different growing regions, I should say. But as you can see, the approximate composition varies quite drastically. Like Dominican Republic, 11.8, and then Ivory Coast is 15.7 protein. Proteins are very important to create the aromatic compounds from Strecker aldehydes in the Maillard reaction in the roasting process. Lipids are obviously probably one of the most important parts in the cocoa bean, and they vary quite widely, as you can see. And then carbohydrates, I figured by difference. Again, super wide variation. So after we pick the pod, we strip the beans with the pulp, we need to allow that pulp to ferment. Fermentation uses yeast and bacterial growth, we know. That bacteria already exists inside the pulp. If you go to a tropical place, were you suggested to eat just the white? They did?
Yeah.
So that was kind of ballsy because yes, it'd probably be fine, but all that stuff is in there and you could definitely get yourself sick.
Didn't die quite yet.
Okay.
Yeah.
Yeah, well, you keep going back to Belize and see what happens. So the fermentation process takes about 7 days. The key production, it is key for the production of the precursors for the chocolate aroma, again, the Strecker aldehydes for the Maillard reaction. There's 3 major phases of fermentation. The first day and a half, anaerobic yeasts are dominant. It's got low oxygen and definitely low pH. This typically happens in bins, very large wooden bins covered with banana leaves to both kind of seal, obviously it's not airtight, but seal oxygen in or out rather, and keep sunlight from getting it, because sunlight obviously degrades aromatic compounds and other important compounds in the process. So the next 2 days to 3 days, lactic acid bacteria are active. These are converting the sugars into organic acids. Typically, the acids are, I lost my notes, I don't have my production, or my presenter notes. Lactic, malic, and some acetic acid. Acetic acids are actually a big problem in chocolate. We'll go into that a little later, but that also was kind of the highest, most tart flavor you probably experienced in the first chocolate I gave you was acetic acid. Who knows what acetic acid is in a household or laboratory setting?
Vinegar.
Boom. So we don't want vinegar in our chocolate, but it's there naturally. After about 4 days, acetic acid bacteria just go nuts, and because of the carbon dioxide and mixed with the carbon dioxide air mixture, it's an ideal environment for these bacteria to proliferate, and they convert alcohols into acetic acid. This is an exothermic reaction, and it gets really hot. It's over 100 degrees Fahrenheit, 50 degrees Celsius. They're actually known to burst sometimes. If the moisture content gets too low, these whole bins will just burst into flames. With the banana, the leaves will kind of dry and burst. So that's a problem you got to look out for. But after about 7 days, 5 to 7 days, the farmers take those beans and they put them single layer and they can dry them either in the sun or in ovens. Lowers the moisture content, stops the processes, and obviously makes it more easy to ship and easy to store and handle. So this is a really cool diagram. This outer section is that white area, the pulp, and this intersection is the bean. And so all of the carbohydrates, pectins, hemicelluloses, organic acid, all the stuff that kind of makes that, Liz, did that have almost like a banana texture, like a fruity texture? Yeah. So those are those hemicelluloses and the pectins and the carbohydrates in that. So all of those things, plus the microbial activity, allow the microbes to make fermentable sugars. Those fermentable sugars are then they're transformed via, anyway, multiple reactions. The bacteria eat them, make ethanol, lactic acid, exothermic reactions, heat. The heat releases all of these caffeine, theobromines, these words that I can't necessarily pronounce, but they are what makes chocolate so awesome in terms of the failing you all here. The anthocyanins, the kind of like the functional properties of chocolate that everybody's like, oh yeah, dark chocolate's good for your health, the same reason red wine is good for your health. Yes, better than red wine because it does not contain ethanol. So anyway, I really like this because it's kind of like a whole, it's a cycle, right? One process creates another process, it all goes around. Until, of course, the pulp, the carbohydrates, the substrate is gone, and then we need to dry and roast and make chocolate. So, talking about roasting, you all have been over the Maillard reaction, probably went home and had nightmares or a headache. It's a super, super complex reaction. I still don't know it through and through, but I know that it takes place right around 50 to 60 degrees Celsius minimum, reducing sugars in the amino groups of proteins or amino acids. And sugars create Schiff bases, create Strecker aldehydes, and those are the constituents of aromatic compounds and the flavoring compounds. This is literally where chocolate gets its flavor. This and the microbial reactions I talked about earlier. So through this process, sucrose that was produced by the bacterial activity is caramelized, and with those reducing sugars creates, again, those aromatic compounds, what gives chocolate its flavor. This is, I think it was from gas chromatography. These are olfactory active volume. It's a measure. So do we know what gas chromatography is? Yes? Okay. So at the end of a gas chromatography, you can pair it with GCMS, you can pair it with flame ionization, you can pair it with a sniffer. I forgot what the actual word is, but you literally put your nose on this thing and you smell the individual constituents that the chromatography has separated. So, and that you quantify in OAV. So we have, what, 1, 2, 3, 4, 5, 6 different constituents, flavor constituents, volatile compounds. Obviously, like I said, acetic acid is quite high. Take note, 52.4 to like 2.6. But there isn't a lot going on there, right? This is an African origin. So this is a commercial chocolate. I have not taken the time to count the different flavoring compounds, but there's a whole lot more, as you can see. And the highest OAV is 840. Acetic acid on this sample was 720. So you can imagine that it tastes quite different, as you all just experienced as well. Try to compare what you just ate to like a Hershey's bar. Quite different, right? And a lot of these, I know for a fact, linalool, phenylacetic acid, and vanillin, these are typically added. I can't speak for these other compounds, but I imagine they're not all just naturally occurring. So it kind of goes to show that you get what you pay for. A single origin chocolate bar would be about $10 to $15 for a bar of like a Hershey size. It is not cheap. So let's talk about refining and conking. This picture comes from Utah State University. This is their chocolate lab, and this is Augustus Gloop. I toured their lab when I was there. It was really awesome to see their process. They gave me a bunch of chocolate. They really wanted me to pursue my PhD there, but Shen bought me one of these, not to this size, but I'd rather have my own than use someone else's. So here I am. So once chocolate is roasted and broken down past the bean to like the nib, then we do what's called a refining process. This is when we reduce the particle size of cocoa solids and the added sugar to somewhere, it's like 10 to 20 micrometers or microns. These are what gets suspended in the cocoa butter to give chocolate those non-Newtonian, those magical properties that Shen talked about. Again, like I went over before, cocoa nibs go to cocoa liqueur, and then we add sugar to make chocolate. The cocoa butter is located within the cell wall, the shell, and the germ of the bean, and so we need to get to that rather than like by crushing, by shearing. And so that's where, if you go back to Augustus here, these are massive stone rollers, and then this whole thing rotates, and the bottom is also stone. So I should have brought my refiner. So it's like a disc, a stone disc with a cylinder, and it just rolls. And so once a nib gets trapped between that, it shears, creates some friction, and that helps kind of evaporate some of those acetic acid, those aromatic compounds that we don't want. And so then we go to conking, which you can't do on a benchtop or home level, but a conking machine, actually, it's almost like a bath for the chocolate, and it heats it to right around like 80 C, and it aerates it, but not for the goal of like carbonation. It's so those air bubbles can kind of grab on or force the acetic acid particles out. So if you go into a room where conking is actively taking place, it's very hard to breathe. Have you ever boiled vinegar, just straight vinegar? Yeah, that's what it's like, because all that acetic acid is released in the atmosphere. So again, it introduces oxygen, and it removes volatiles and some of the short-chain fatty acids that are produced in those bacterial reactions. And if you look here, before conking, it's very simplified, but obviously like you have the nibs on probably like a molecular level, not molecular, but macro level, and the sugar particles, and conking